Hello, SM2. Alright, let's get right into it. So our first lesson that we're going to officially cover in this class, 1.1 absolute value functions. So in our review, we talked about linear functions. So this is a different sort of a function. It behaves a different sort of a way, but in some ways very similar to the linear function. Before we talk about the function, though, let's talk about what it means for what an absolute value is. What is absolute value? So to kind of describe it in a situation in words, so let's say that we have ourselves like a line right here, and over in this direction represents a positive direction. Over in this direction is a negative direction. Really, we're just saying you can go this direction or this direction. However, let's say we go over this way to the negative 5 unit spot. So basically we're saying we're going to the left 5 units. Now when I ask you how far did you travel, you don't tell me, well, I traveled negative 5 feet. There's no such thing as negative distance like that. You traveled 5 feet, but you traveled in the left direction, in a different direction. So basically, what absolute value means is that it is a way to state net positive results. Alright, so what an absolute value is going to look like is you're going to see two lines and you're going to see a value in between those two lines. So for an example, let's say I ask for the absolute value of negative 5. Well, the absolute value of negative 5 is equal to 5. It's equal to the positive number of whatever value that is. The absolute value of negative 3 is equal to 3. And the absolute value of 2 is still 2. So that's how we get rid of the negatives when we're talking in situations where the sign doesn't matter. We just want to be talking in positive terms. So that's what absolute value is. So let's go ahead and draw in this parent function of our absolute value function. So I already have here, this is what the parent function looks like. F of x is equal to the absolute value of x. Don't get that confused with the linear parent function, which was f of x is equal to x. Again, we have the signs, which means we're talking about absolute value. Alright, so in order to graph this out, let's make a set of inputs and outputs for this right here. So let's try negative 2. So our function is f of x is equal to the absolute value of x, and we're going to try in the input of negative 2. That's the absolute value of negative 2. Well, we said up there that this is just equal to 2. Now, let's try f of negative 1. It's equal to the absolute value of negative 1, and that's equal to 1. So notice that anytime we input like this negative value in here, we're just getting a positive value. So that's pretty cool. So that's what an absolute value does. So now let's go ahead and do 0. Which is equal to the absolute value of 0. Well, that's just 0. Alright. 1 is equal to the absolute value of 1. That's just equal to 1. So an x is 1 or y is 1. And last, let's try 2. Absolute value of 2 is 2. So an x is 2, y is 2. Let's go ahead and plot our points on this graph right here. So, at negative 2, our y is 2 right there. At negative 1, our y is 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. So you can see here, as we go from negative to 0, and then 0 to positive, you can see our y values are the same. See how symmetrical that is? You see, you have 2, you have 1, you have 0. So our graph is symmetrical. Now let's go ahead and draw our lines. Just like that. So it's a V-shaped graph and it's symmetrical. So when I say it's symmetrical, I mean you can reflect it across this line and it would be the same line. They would be on top of each other. So that's some characteristics of our absolute value function. It is V-shaped. It is symmetrical. Alright, so that's what it looks like. One other characteristic I want you to know is right here, the point where they meet together, where this line of symmetry is, that is called the vertex. And the vertex occurs at a certain point. And in this case, the vertex right here is at 0, 0. And now let's talk about the domain and range. So our domain, we're talking about our x values. And our range, we're talking about our y values. So our x values right here, where does our graph exist? For what values, x values, does our graph cover? Well, this graph is going all the way that way and will go all the way that way to infinity and negative infinity. So our domain covers negative infinity to infinity. But our y value right here, you can see that our graph never goes below this line right here. Never goes below the x-axis. We don't have any negative y values. So our range starts at 0 and then just goes up to infinity. Starting from 0 and we'll go up that way. Okay, this is just a note telling you the similarities between the review and what we're doing here. Just like the linear function could undergo transformations, and that would be in the form of y equals mx plus b. This would change the slope and the y-intercept. Likewise, the absolute value function can also undergo transformations, and that's what we're going to talk about right now. So here, this is a horizontal shift. So what does a horizontal shift look like? When you have a horizontal shift, your function will look something like this, where inside the absolute value lines, you're going to have an operation and a value, a constant in there. And so whenever you see this, your graph, your parent function, will shift to the left or to the right. Whenever you have a minus sign right here, you're going to shift to the right. And I know that sounds a little weird, because whenever you think negative, well, these are the negative numbers, right? Well, not in this case. Whenever anything that happens inside our lines, we read it in a negative sort of way. So not in a negative, but in an opposite way. So when we see negative, you're going to shift to the right. When it's positive, you're going to shift to the left. So always remember that. And whenever you have a constant, whenever you have an add or subtract inside the absolute value lines and a constant, you're going to shift it over. And how much do you shift it over? You shift it over however many units this h is. So you'll shift it over h units. So what does that look like? So right here, I already have our parent function. Now let's go ahead and graph this function that we have. So like we said, we have a negative number right here. So when it's negative, we're going to shift to the right. So we're going to say that this is a horizontal shift to the right. How many units? H units, or in this case 2 units. And so what an easy thing to start with is your vertex. So our vertex right here is at 0, 0, but we're going to shift it over to the right 2 units. Just like that. And everything in this graph is going to shift to the right 2 units. So as an example, I'm going to put in 1 into our equation. So I do g of 1. So I'm going to get the absolute value of 1 minus 2. Well, that's going to equal the absolute value of negative 1. And the absolute value of negative 1 is 1. So when my x is 1, like right here, our y value is going to be 1. Let's go ahead and connect those dots, draw on our line. And like we said before, that this is symmetrical. So going off in this direction, we have another line just like that. So you can see that this entire graph right here has been shifted over to the right 2 units. Now you can go ahead and try this function right here, this graph right here on the same graph that you have to the right, but that's for you to see and do on your own. Just as a tip, remember that this sign right here, if it's positive, you're going to shift it to the left h units. And last but not least, what is our range? Well, our range hasn't really changed, and neither did our domain. The domain of absolute value functions is actually always going to be negative infinity to positive infinity. It covers all the x values. And our range in this case, well, we're still starting from the 0 and moving upwards. So our range is still 0 to negative infinity. Alright, now we're going to cover vertical shifts. Now, like we showed above, the difference between a vertical shift and a horizontal shift is that a vertical shift, your operation and your constant are outside of the absolute value functions. And in this case, we don't have to read the operation backwards. Meaning when you see a negative sign, that means you're naturally going to move downwards. And you're going to move downwards k units. So whatever value k is. When you see a plus sign, you're going to go up k units. So here I have my parent function. Let's go ahead and graph this function right here. So let's go ahead and put in 0. Let's just try sorry, we'll do that later. But in this case, let's start with our vertex right here. So our vertex is still at 0, 0. But we're saying that this right here, this plus 3, we're going to do a vertical shift up 3 units. Because it's happening, the operation and the constant is outside of the absolute value. So we're going to move our everything up 3 units. 1, 2, 3. Alright, now let's plug in our x value at 1. So if we do v of 1, we get the absolute value of 1 plus 3. And the absolute value of 1 is just 1, so we get 1 plus 3, which is equal to 4. So at 1, x is going to be equal to 4. Okay, and we know it's symmetrical because of the absolute value, so likewise in this direction, we'll see it look like that. And notice that on each side where our y value is 4, the function for x equals 1 and x equals negative 1, it's still going to be 4. Alright, let's talk about our range. So again, here, this function down here, absolute value of x minus 3, that's something for you to do on your own. Just remember to do the shift in the right direction and over k units. And our range right here, well, you can see that our since we shifted up right here, our function no longer will hit any values less than 3. And so, what we say is that the range is from 3 to infinity. And we do this closed bracket right here because we include 3 in our solution set. 3 is included in here. And I actually probably should have drawn a bracket up in these ones right here. This is actually a bracket right there. We'll include that right there. So that's our range. We don't exist anywhere below the 3. Only 3 and upwards to infinity. Okay. Now we're going to talk about shrinks and reflections. So to kind of speed this up and not take too much time, a shrink happens. Let's go ahead and just graph just a couple of these points. So let's say we plug in a negative 2 into our equation. Now right here, this is what a shrink or a stretch looks like. We now have an a that's being multiplied by our absolute value, And so that's what it looks like. So let's say, for instance, if I plugged in negative 2. So h of negative 2, that's the function that we're looking at. So h of negative 2 is equal to 2 times by negative 2. Well, the absolute value of negative 2 is just 2. 2 times 2 is 4. So like that, when x is negative 2, y is 4. Move that up. Alright. Now, when we put 0 into our function, so when x is negative 2, h of x is 2. If we put 0 in our function right there, we're just going to get 0 in there, so we're multiplying by 0. So it's still, our vertex didn't change. And if we did x of 2, when x is 2, so h of 2, we'll get 2 times the absolute value of 2. It's equal to 2 times 2, which is equal to 4. There you have it. So this is what a stretch looks like. You can see here that we have a steeper slope on both sides. It's steeper than our parent function. Just like that. And so what we say here is that there is a vertical stretch by a factor of 2. Just like that. By a factor of 2. That's what we multiplied it by. Now down here I have one more equation. I'm going to graph this out. Feel free to do it yourself, but it's by 1/2, and I already have values right here. So if I were to plot those, when x is 1, my y value is 1/2. That should be 1 right there. And when my x is -1, my y value is also 1/2. Just like that. So you can see the difference here is that my absolute value function here in this case is below my parent function. So why is that? Well, the reason why that is because in this case our a value is greater than 1. If you think about what this line is right here, this absolute value function, the slope of that line is -1, because this line right here is y equals x, and this line over here is y equals -x, right? So that is what the absolute value function is, pretty much. And so our m value is 1 in these cases, but up here we have it as 2, and down here as 1/2. So that's the difference between a stretch and a shrink. So this one is a vertical shrink by a factor of 1/2. And so when is there a stretch and when is there a shrink? When a is greater than 0, you're going to have a stretch. When a, I said that wrong. When a is greater than 1. But when a is less than 1, you're going to have a shrink. So that covers our stretches and our shrinks. And again, I'm kind of going to speed through this one because this one's pretty straightforward. When you have right here a reflection, when you have a negative number, so this is really -1, right? When you have a negative number being multiplied by the absolute value function, you're going to cause a reflection across the x-axis. Like that. So that is what a reflection does. A reflection will look like a negative number outside of your absolute value function. Okay, so now we're going to move on to this last example, but in this case we're going to be doing a combination of everything. So you can see right here, this is a combination of all the transformations. And this is what we're going to work with right here. Okay, so in this function right here, let's identify where the vertex is. So let's identify the shifts to do that. Well, right here we have something inside our absolute value functions. We have a -1. We're subtracting a 1. And since it's inside, we're going to read it backwards, right? So we have a horizontal shift to the right 1 unit. Alright, now we have a k right here, and it says +3. So this is a vertical shift up 3 units. So where is our vertex? If our vertex is starting here, like that, and we're going to the right 1 and up 3, that's where our new vertex is going to be. Okay, so now let's go to the next question. Well, let's first, our vertex is at 1, 3. So our next question is there a stretch or a shrink? We do have an a value right here. It's negative 2. So a is 2, greater than 1, so we will have a stretch. A vertical stretch by a factor of 2. Is there a reflection? Now we said that there's a reflection if this a value is negative, and in this case it is negative. So yes, there is a reflection. Now to finish this, let's go ahead and graph points. So this line of symmetry that we have is going to happen at the vertex. So let's graph a point that happens right here. So this is 2 at x equals 2. So let's plug 2 into our equation. So g of 2 is equal to negative 2, absolute value of 2 minus 1 plus 3. That's going to be negative 2 times by 2 minus 1 is 1. Plus 3, absolute value of 1 is 1. So then we have negative 2 plus 3, and then we're going to get 1. So when g is 2, y is 1 right there. Let's go ahead and graph that. And we know that it's symmetrical. So on this side of the line, if we go over 1, our y value over here was 1. So our y value, 1 unit over this way, will also be 1 because it's symmetrical. And look at that, we have an upside down V-shaped absolute value graph, which confirms that yes, we did have a reflection, right? Because now it's an upside down V. And so now we've covered all the transformations in just one equation. So now what's left to answer is the range. So the range, well, we know we're covering everything below down here, but how far up do we go? So we go as far up as this value right here, and we know the y value right there is 3 because that's our vertex. That's the y value of our vertex. And so we start at 3, we don't go any higher, but we go below. So this should be a closed bracket, 3 to negative infinity, and that's our range. So I know we kind of covered that pretty quickly, but it should be pretty easy for everyone to do. If you have any questions, of course, come to class prepared to ask those questions, and we'll have a better discussion, a more deep discussion, and we'll do more examples to help everybody. Alright guys, well, I'll see you in class. Thank you.